Hello everyone, and welcome to Knowledge Discovery and Data Mining, the third webinar of the Charles Sturt University short course. My name is Guy Coward and I'll be your MC, and your mentor this week is Michael Bewong. Before we begin, as usual, some housekeeping. We encourage the asking of questions and the use of chat during the webinar, and we use two methods to do so. We ask that you direct all course relevant questions to the Q&A section, and that you send all administration type questions to the chat, just as usual. You can chat with panelists only or to all of your fellow students as well, and you can make that choice by toggling through the drop down box once you've opened the chat log. Last couple of weeks there's been some really useful chat in there. People who have been embedded in the industry or using data science more accurately already, who can help with people that are new to the field. So any queries you have can be answered in there. We'll have a Q&A session periodically, or if a question is particularly relevant, I'll interrupt Michael. Leif is around as usual for the IT Masters support role. He's responsible for the course page, which is where you'll find all the materials, readings and discussion forums and quizzes. And if you have any questions, feel free to contact us using the details on that page. So now Michael. Michael's a lecturer at Charles Sturt University in computing, and he's been working in knowledge discovery and data mining for ages. He's a PhD in computer and information science, and he's just come back, as you might have heard last week, from a conference in China. Welcome, Michael.
Thank you very much, Guy. I hope you can all hear me all right.
Clear.
Excellent. So as Guy mentioned, I'm currently a lecturer at Charles Sturt University. I only joined a couple of months back. Prior to that, I've been working on a couple of research and industry projects in data mining. I think the most recent project I've been working in data mining is solving the problem of topic discovery from unstructured data, particularly text. So hopefully some of that stuff should be useful as we go through the discussions today. So I'll just jump onto the slides. So again, welcome again to the lecture series. So this is the third one. Zahid Islam has given the first two, so I'm continuing on. Just to help us to kind of understand what we're going to be doing today, I'll probably just recap some of the stuff that Zahid might have gone through with you in session 1 and session 2 before we really jump into stuff that we're going to do today. So in session 1, I believe Zahid must have introduced the concept of data mining, which really is using a suite of tools to discover knowledge from data to solve real-world relevant problems. Now, these suite of tools can be machine learning tools, can be statistical tools, and so on and so forth. So in that sense, there are three main things you probably want to consider as a data miner. So the first thing is the what. So that involves the tools. Now, these tools broadly come from the domain of AI. Okay, so within AI, we may have machine learning, robotics, probabilistic reasoning, knowledge representation, computer vision, and so on and so forth. Now, all of these tools are relevant to the data miner in terms of collecting data, analyzing the data, and making sense of it. The second point is the how. So that is how we combine these tools together into a functioning system. So from the industry perspective, this would be some sort of software engineering. So as a data miner, it's usually relevant to have some little knowledge about programming, because that allows you to build prototypes or even to test your models once you have developed them. And of course, once you have a prototype, then the software engineer can actually convert that into a production level code into a software or an app. And then the final thing is the why. In fact, this is the most important part of data mining. It answers questions such as, why are you using this model? Why are you combining these models in this way? Why are the results the way they look? Why are you using this data to solve this problem? This is the most important part, and that is where much of the analytics is concerned. I also believe that in session 1, you looked at the data mining lifecycle, of course, from data collection process all the way through knowledge reintegration. In session 2, you probably looked at decision tree classifiers, In decision tree classifiers, there are two major things to consider: how to build a decision tree, and then how to use a decision tree to make predictions. So generally, when we build decision trees, we call them, or we call the algorithms for doing that, decision tree induction algorithms. There you might have looked at some of the criteria for deciding which nodes to use to build a tree, and so on and so forth. These are some details that we cover in the subjects when we actually deliver it on campus. So today we are looking at knowledge discovery. So that really deals with making sense of the models that we have built and what relevant information we can extract from the model. So in this case, we look at how we extract the knowledge or relevant information from the decision tree classifiers. In subsequent weeks, we would look at decision support systems, which actually relates to how we put all of this into a system that aids in making decisions. So hopefully we should be able to cover much of what we have decided to cover. So going on to today's lecture outline, there are three main things that I would like to cover. So the first thing is the purpose of knowledge discovery, where we would look at the importance in how we can actually get knowledge from data sets. Then we'll look at the various techniques. In fact, when we talk about the various techniques, we'll probably focus on decision tree classifiers because that is what has been explained in the past. However, during the actual delivery of the subject, we will look at other techniques as well, but I'll still mention some of those techniques. And then the third thing is the interestingness of the discovered knowledge. So when we talk about interestingness, we're looking at the importance of the knowledge that we are discovering. So for example, if you ask me the question, why insects get caught in a spider's web, okay, that's just because the spider's web is sticky. But a more interesting question would be, why don't spiders themselves get caught in their own net? So that is a more interesting question, and that is really the aim of knowledge discovery. Then we'll look at how all of these three things.
What's the answer? Sorry, Michael. that's such a good question.
That is because they release an oily secretion that allows them to glide over the spider's web. So.
Cool. I had no idea. Thank you.
Yeah. So, and then, but we'll not be talking about spiders in this lecture. So. And then we'll look at how we combine all of these three things, or how it is utilized in a case study, and then we'll consider one specialized framework as well. All right. Any questions after this point? I guess I'll just carry on.
No, we're all good. Thanks.
Excellent. So purpose of knowledge discovery, of course, the main aim of data analysis is to make sense of the data. So that is really knowledge discovery. This knowledge can be expressed in various forms, so in the forms of patterns. For example, we may have a model that says every 9 to 10 years, property values will plunge. That is something we call time series patterns. We may represent them in terms of logic rules. For example, we may say that if single-way airline tickets in a state rises, then property values will decrease. Okay, so this type of rules are if-then rules. So that's what we call logic rules. We may also consider knowledge in terms of mathematical expressions. This often relates to the specific classifier of support vector machines. Some of you know it, some of you don't. But essentially what that means is that you have a mathematical expression, and within the expression, you have coefficients. So these coefficients are considered weights. So the heavier the weight, the more important the attribute is for predicting the class. So in that sense, when you look at the weights, you may be able to use that to interpret the model in some sense. Then, of course, we have trees, which are really nice ways to visualize logic rules, because then you can see the pathways from the root of the tree down to the leaf. So in doing this, we probably wanted to look at three main considerations. So the first thing is we want to look at the objective of the knowledge discovery. So in this case, the business needs for the discovery, okay? Then we want to look at the tools that we'll be using for the discovery. So as a data miner, you may know how to use all these many tools, but you need to use the right tool for the right problem. So whereas in some cases you may use a naive Bayes classifier, in other cases you might want to use a decision tree algorithm. So you need to consider the business objectives, and then you need to link that to the tools that you're actually using. And then finally, it is the knowledge that we discover, so the usefulness of the discovery. So just going through an example of some of these points that I've raised. So this is an example of a data set that relates to diagnosis. And in this case, the domain values for diagnosis is either cancer or non-cancer, okay? So an objective could be we want to find the attributes that are indicative of cancer. Or it could be that we want to predict whether someone has a likelihood of having cancer or not. So that is a clear business objective. In terms of tools, we may use simple correlation. Now, simple correlation is more of a statistical tool, and often we use it in data pre-processing, but for the purposes of this lecture, I just use it as one of the tools, okay? So in this case, when we talk about simple correlation, we're looking at how the values of one attribute, in this case, tobacco, behaves with diagnosis. So so here we are saying that whenever tobacco is no, then we have a non-cancer. So in this case, we can say that the values of diagnosis are related to, correlated to the use of tobacco, right? We may also discover a pattern, for example, between alcohol and tobacco. We may see that whenever alcohol is high, tobacco is also high. When it's low, tobacco is also low. Now, there are various algorithms for calculating or determining the correlation values for categorical attributes, which is this case. We often have the Kramer-V test. For numerical values, we may have the Pearson's test, right? So whenever you have a data set, one of the things that you may do would be to consider the correlation, because that gives you initial idea about how the data is behaving and how you can possibly use that to discover knowledge, in other words, make predictions, okay? So once we have identified the tools and use them correctly, then we can extract make some sense of it. So for example, we may say that we can use a correlation that we found between alcohol and tobacco to reduce the features. So often when you have a data set, you may have hundreds of attributes of hundreds of features, in that case, the columns, right? And there are a few reasons why we like to reduce the features. The first reason is that we want to reduce the complexity of the model, because the simpler the model, the more easy it is for us to interpret it or to discover sense or make sense of it. Second reason is efficiency. So if you have to go through all the attributes, algorithmically speaking, then if you have one less attribute, then that's one less round of going through the attributes. So we can make sense of that knowledge that we've just found, the fact that alcohol and tobacco are correlated, to reduce the features. We could also use that to actually predict missing values. So for example, if we notice that each time alcohol is low or none, tobacco is none, then we can say that, well, if an individual decided not to put a value for tobacco, then we can use the fact that we know that the individual's alcohol is low to kind of estimate his tobacco value. Now, again, this is where it is important for the data miner to do this carefully, because sometimes this may not necessarily be the case, all right? So for example, you may not necessarily say that if someone has high alcohol or consumes more alcohol, that person automatically smokes. That may be true, may not be true, all right? So that is where you need to think a little bit more about it. We could also use this discovery for social intervention. So if we want to tackle the problem of smoking, then we might consider the fact that they are correlated to also tackle the problem of alcohol, because there's some sort of relation, right? So these are ways in which we can discover knowledge and make use of that knowledge. So in this example, we've seen that we can discover knowledge using simple correlation, and then we can use that knowledge to make something, do something meaningful. Okay, so at this point, I believe it's a bit clear as to what the purpose of knowledge discovery is. So my plan is to look at some of the techniques, and particularly to focus on decision tree classifiers and how we can actually extract knowledge from that. Are there any questions at all at this point?
Yeah, just a quick one.
Yeah.
Could you just quickly go over feature reduction again? Scott's asking, what was that? So that was, my understanding was sort of condensing the number of columns.
Yeah, so that's correct. So usually when you have a data set, so this is a simple data set, so we have only 5 attributes or 5 columns, but in practice you may have hundreds of columns. So when you have hundreds of columns, analyzing them becomes a little bit challenging. The complexity of the model also increases. So for example, I mentioned, I talked about support vector machines. So in support vector machines, you have an expression for each attribute, basically. So if you have 100 columns, then you have 100 weights and 100 values for each of the columns. And so interpreting that model would be more difficult than interpreting a model that has only 5 columns. Okay, and then also in terms of efficiency. So if the algorithm needs to check each column, if you have less columns, then that means you have less rounds of checking to do. So that's basically the relevance of doing feature reduction.
Awesome, thank you.
All right, so going on to techniques for knowledge discovery. So generally when we talk about data mining, we often talk about supervised knowledge discovery and unsupervised knowledge discovery. When we talk about supervised knowledge discovery, that means that our training samples are labeled. Now, training samples are nothing but the rows or records in the data set that we are going to use to build the model. Now, when they are labeled, that simply means that the target class or the target attribute that we want to predict has a label. So previously we saw a data set where the diagnosis was a target label. So we want to predict diagnosis of an individual. So that becomes your class attribute. So when we talk about supervised knowledge discovery, that means that your training samples have those labels for the diagnosis column in that example. In terms of unsupervised knowledge discovery, that simply means that you do not have those labels. And there are many instances where you will not have those labels. So examples of techniques for supervised knowledge discovery include decision trees, support vector machines, regression analysis, rule-based classification, ANN, and so on and so forth. In terms of unsupervised knowledge discovery, we have clustering, association, rule mining, anomaly detection. In this particular lecture, I focus on decision tree induction because that is what perhaps has been mentioned to you in the past couple of weeks, and it's relatively much easier to understand. So, assuming you know how to build a tree, well, I'll briefly go over the points in building a tree. So generally, when you build a tree, there are a couple of challenges. First of all, you need to select which attribute that becomes your root node. So when we talk about a tree, we are talking about nodes and edges. So this is a node, this is an edge, this is sort of a node, right? And then the edges connect nodes to connect various nodes. So in this case, we need to determine which attribute will be represented in this node, all right? But there are many attributes. So here, when you actually go into details of decision tree induction, there are several techniques for selecting the attributes, okay? And then you may also have intermediary nodes. So from tobacco, you may go to inflammation, and then you may go to alcohol before you actually get to the leaf nodes. The leaf nodes generally represent the class value for the records within that node. So here, with that, assuming that we know how to build trees, I just build a simple tree where I have the root node to be tobacco, and then we have some leaves, okay? So if we look at the data set, we see that I have split this based on the domain values of tobacco. So domain values means that the values for tobacco. So tobacco has 3 unique values: high, no, and then moderate, okay? So that becomes my branches. And then we look at the leaf nodes. For each instance where there's a high on tobacco, there's a diagnosis of cancer. So here I have the value cancer, and then with what we call a support, which I'll explain shortly as to. For moderate, we also have a similar situation. And then for non-cancer, we have 6. So we have cases for tobacco being no, no, no 6 times. And then for each of those cases, they are non-cancer. So that is our leaf nodes. Now, so if you have a decision tree like this, you may extract some logic rules from the tree. And that is nothing but the pathway from the root node down to the leaf. So here, the first one could be that if tobacco is high, then cancer is yes. So that's the first logic rule. If tobacco is moderate, then cancer is yes. That is the logic rule. And then if tobacco is no, then cancer is no. So that is the logic rule. Now think about this. If you have 100 attributes and several records, you can potentially have a bigger, much bigger tree. So being able to extract some rules from the tree and making sense of it helps a great deal, okay? And I'll explain shortly how and why we select some rules to make sense of it. So in this case, we just say that we have these 3 rules. So as I mentioned, that leads me to interestingness of discovered knowledge. So that tells us how and why we select some rules based on all the rules that we've collected and based on the objective of the problem we are trying to solve. Up to this point, is there any question at all?
No, that was all quite clear. Thank you.
Excellent. All right, so interestingness of discovered knowledge. Now, of course, when you have a decision tree or decision forest, you may have many logic rules, okay, in the range of thousands, because you are looking at every pathway from the root node down to the leaf. And there are so many pathways that you can have, and each of them will form a logic rule. So there is a need to choose those that are more important. In other words, to rank them. And then, because obviously it won't make sense to go to your manager and say, hey, I built a beautiful tree, there are 1,000 rules. Okay, what does that mean? So there's a need to say, okay, I built a tree. Out of the tree, there are 3 important things we need to consider. Those 3 important things are the rules that you have actually extracted. So the question is, how do you extract them? Because you may not be able to manually look at all the 1,000 rules and then extract the important ones, right? So we need to define some metrics. Now, there are many metrics out there. Researchers have proposed several ways of ranking rules. In this lecture, we'll just consider 4 of them. Again, as a data miner, you get the option to choose, right? So that can be a blessing and a curse as well. So just going through an example of each of these metrics, so I want to talk about support. Support really gives an indication of how often the rule appears in the data set. So in other words, the number of records that support the rule that you have generated. So in this example, if the rule says that whenever tobacco is no, cancer is no, then when we talk about support, we're looking at how many instances here actually support the rule. So in this case, we notice that there are 6 instances out of the 10 records that actually, for which the rule holds. So we can say the support is 6, or we can say the support is 60% if we take it as a percentage. We may also look at another rule, which says whenever information is no, then cancer is also no. In this case, our support similarly can be calculated to be 4 or 40% if we take it as a ratio of the number of records in there. So here, based on support alone, we may say that the first rule here is perhaps more important than the second rule. So if we had, if a knife was held to our throats and we had to choose one, then we'll probably go with the first one, all right? So the second metric that we probably talk about here is confidence, otherwise known as reliability. So this gives an indication of how often the rule is correct. So for all instances containing the antecedents is the part on the left-hand side of the rule. For all instances of it, what ratio of it contained the consequence, okay? So for example, here we see that we have 6 instances of tobacco being no, and the consequence, we also have 6 instances of non-cancer. So in this case, we can say that when we calculate the confidence, we may say that that is 6 out of 6 and that is 1, and therefore we have a confidence of 1 or 100% if we take it as a percentage. On the other hand, if we calculate the confidence of the second rule, we notice that on the with the antecedent, we have 1, 2, 3, 4, 5 instances on the left-hand side of the rule, but on the right-hand side of the rule, we have 4 instances. So in this case, we can calculate the confidence as 4 out of 5, which works out to be 0.8 or 80%. So that tells us that now this is quite important in the sense that if you calculate your confidence and your confidence is quite small, then that could mean that the combinations of inflammation and diagnosis in this example is just random, okay? So that means that the rule is not really strong in that sense. So again, if we had to choose between these 2 rules based on confidence values, then obviously we go with the one with a higher confidence value, which is 100%. So that's that with confidence. The other metric that we can consider is conciseness. So as I've already mentioned previously, is that when we have simple models, it is much easier to interpret than when we have complex models. Now, if we have several attributes, well, in this case, this is quite simple. You only have 2 attributes on the left-hand side here. But there are cases where when you trace the path from the root down to the leaf of a tree, you may have probably 50 attributes on the left-hand side of the rule. And in that case, that can be a little bit tricky to deal with. So if you have any 2 rules and they both have the same confidence and support values, then you probably want to go with the one that is more concise because that is more interpretable. And then finally, we can talk about actionability. So you can discover several rules, but in choosing the rules, you also want to choose rules that can have that can be used at the business end. Okay, so for example, in these 2 rules, we have a rule of tobacco being no, cancer being no. It's a valid rule, and then we have another rule: inflammation being no implies cancer is no. Also a valid rule. But if you were to go out and try to intervene on prevalence of cancer, well, it's nothing you can really do about inflammation, right? But there's something you can do about tobacco. So in this case, the first rule is more actionable than the second rule. So if you have a set of rules, you rank them based on your confidence and support. You still also want to look at which rules are more actionable for the managers to take and then act upon them, or whatever the policymakers or whoever is in charge in that sense. So as far as interestingness of discovered knowledge is concerned, there are several metrics to actually measure their interestingness. In this particular lecture series, we've only looked at 4. In the subjects that we deliver on campus, we look at a few more than that. So if there are any questions at all about what we've looked at in terms of interestingness, I'm more than happy to take them.
None coming in, but feel free to chuck some info. So I'm pretty interested in some other metrics. We're going pretty well for time.
Okay, so there are metrics like peculiarity or novelty or lift or conviction. There are so many. So for example, when we talk about lift, right? Lift is Let me see if I can borrow a formula here. So lift, rather than calculating the ratio between the support of these two to the support of the antecedent, it calculates, maybe I'll just get a pen, all right? All right, so I just make life easy and represent this by X and represent this by Y. So when we talk about lift, right, we are looking at the support of X and Y divided by the support of X times the support of Y. Now, this looks simple in relation to this, but it has profound implications. Now, what we are doing here, really, we can rewrite this as a probability. So for example, this one represents a probability of picking the attribute value X. This represents the probability of picking the attribute value Y. The product of it represents the combined probability of picking both of them, right? So if you know a bit about probability, then when you consider selecting two things together, you often multiply their probabilities, all right? If you consider selecting either or, then you add their probability. So in this case, we're looking at the probability of selecting two things together. Supposing we had no knowledge about the data set, then the probability of selecting inflammation and diagnosis together would be the probability of inflammation alone times the probability of diagnosis alone. So that is represented here. Now, this one gives us the actual observed probability of selecting those two things together. So when we divide the two, that tells us whether the X and Y are independent or not, right? So that is another measure as well.
Cool. It's about the most fun technical intervention we've had on a slide in a short course as well. So, so that's very exciting.
I'm glad it helps.
We've had a couple of questions come in while we've been talking as well.
Right.
What confidence percentage do you generally consider to be viable?
Okay, so this is where the data miner has to decide. So sometimes you have data sets and then you may set a threshold of say, okay, 50%, and then you get nothing. And then, so then you have no rules to work with. And sometimes you may set a threshold of 50% and you have 500 rules, all right? So generally, when people say data mining is a science or an art, the art part of it is being able to fine tune these parameters. And that is where your analytical skills comes in, to be able to actually define what is a good confidence value for a particular problem. And of course, your ability to justify that, that's what makes you a good data miner. So I'm not able to say off the top of my head what is good. It really depends on the problem we're trying to solve.
As usual, the answer is maybe. And I assume that the answer would be the same for the last question we'll take for now. And it was talking about the actionability of tobacco and alcohol versus, you know, inflammation. These would all come into sort of the analytical, theoretical side of things as well.
Yeah, exactly. Yeah, and in cases like actionability, then of course you probably want to consider, if you have a few rules like tobacco intervention, alcohol intervention, then you also want to consider the cost component as well. And you may build a model that tries to optimize this cost as well and use that as part of your decision making. And so when you look at all of this, in lecture series 1, you saw how the cycle goes back to knowledge reintegration. And so generally when you work in industry for a company and then you have a data mining project, the project does not just finish with you building the model. So usually you might build a model and then the model might be deployed, and then over time you reintegrate what you've learned into the model building and improve it as you go. So yeah. All right, so going on to the case study, we'll try to look at how some of these things are playing in this case study. So this is about brand switching pattern discovery. And interestingly, Zahid, who took the first 2 series, he did some work on this as well. So we'll just look at some of his findings. So here, just a bit of background. In 2011, we had about 25 million mobile subscriptions. And of course, that works out at about greater than one mobile subscription per person. So an interesting problem or question is whether there are any patterns in terms of people switching telco providers, and whether there are any indicators to predict the likelihood of customers switching in that sense. Of course, you can work that out. This could mean millions of dollars for a telco company, for example. So a survey was conducted by Emasim. So Emasim, I think, is a telco company. And what they did was that they conducted a survey, posed a couple of questions to people that they thought would be leaving their telco company for one reason or the other. And then after 12 months, they interviewed these people again to actually see whether they switched or not. Now, again, in industry, as a data miner, you may not necessarily be the one designing the survey. You may work in teams where, for example, you may have a software engineer that might write a piece of code that scrapes information from a website, or you may work with some statisticians that may have access to some data and they may give that data to you. So as a data miner, one challenge that you may have in industry is how you actually take data from various sources, be it your colleagues or be it from a statistician, how you convert that into a format that can be fed into your model. Okay, so that is one major challenge. And I was speaking to one experienced data scientist, and he said that that takes probably about 70% of your time, all right, 70 to 80% of your time before you actually do the modeling. As far as the work that Zahid did on this was concerned, they built some decision trees and forests, and then they discovered a couple of interesting trends. Of course, several trends were discovered, but for discussion purposes, we only look at the most interesting things. So again, these are nothing but logic rules, all right? Or at least logic rules with probabilities. So in terms of males, it's realized that the younger males had a higher probability of switching once they decided to do so. So about 75% would switch once they decided to do so. Older males was a bit lower, so about 54% would switch once they decided to do so. On the other hand, in terms of females, only about 37% would switch when they actually said they were gonna switch. So you take this, and then from the business perspective, you say, well, if you have $1 to spend on either a male a client who is disgruntled or a female client who is disgruntled, you probably spend it on the male, because at least the data is telling us that the male is likely to leave. So this can be wired into how they design the product. For example, you may offer deals to males who are probably going to leave, and then you may offer loyalty points to females because they are probably going to be more with a telco company and that sort of thing. So this is information that you can then use, and of course, with the expertise of marketing people, you can use that to actually reach your business goal. So this is just one case study, and it was done using decision trees. So some of the stuff that we've seen. Any questions at all about this?
Just more of a comment from Scott, talking about, you know, banks that don't appear so much to using this example sort of invest in keeping customers. It's about getting new customers. And I suppose studies could be made to sort of, again, sort of find the best way to spend the budget that you have.
No, absolutely, that's true. That's really true. Because, I mean, if you consider people when they actually join a bank, people rarely change banks, right? So people will be with a bank for the rest of their lives. So banks will generally want to get in new people. So I think 2 years ago, there was a news bulletin about one bank. I can't remember the name. And what they were doing was they were introducing, financial literacy to kindergarten and primary school students, because the idea was that, of course, they were trying to get them to open like savings accounts. And once you start an account from that age, you're probably going to keep it till you die. And so that is a really brilliant marketing strategy. And some of this stuff, you can get that from the data. Right? All right, so now I want us to look at a specialized framework. This framework was developed by Zahid in 2017. Now it tries to solve one of the challenges relating to determining the interestingness of rules, okay? So as I mentioned, you have so many interestingness measures. Which one do you use and how do you use it and how do you even combine them? So if this one has a support of 5 and this one has a confidence of 50% versus this one has a support of 100 and a confidence of 30%, how do you actually combine this to select your rules? So that is what this work tries to do. And in general, when we do research in data science or data mining, these are the types of problems that we try to solve. So just to give you an idea of how the framework works. So first of all, it aims to, it starts by dividing all the logic rules into groups based on their majority class. So what do I mean by majority class? So for example, when you build a tree, in the previous example that I showed, the leaf nodes were either cancer or non-cancer. But typically when you build a tree, you wouldn't have a clear-cut distinction like that. For example, you wouldn't have a leaf node that is fully non-cancer or fully cancer. You may have a probability, all right? So that may be, for example, 80 to 20 probability, or that may be 90 to 10 or 70 to 30 or whatever. Now, the majority class is simply the one with the highest probability. So if you have a leaf node that has 70% cancer and 30% non-cancer, then your majority class for that leaf node is cancer. In the case that you are doing a binary prediction, in that, what I mean by binary prediction is that your target variable, in this case diagnosis, was either cancer or non-cancer. So that's binary. But you may be doing predictions that involves maybe colors or size. And in those cases, you may have multiple class attribute values. So your majority or the number of groups that you have will not be 2. You would have more groups, the same number of groups as you have the number of attribute values for the class. Okay, so from our example, this dividing the logic rules, into groups, you would end up having 2 groups because you only have cancer or non-cancer. Then the next thing the algorithm does is that it actually derives subsets from these 2 groups. So first of all, you have these 2 groups, right? So one is cancer, I just put C, and then other is non-cancer, I just put NC. And then from that group, you actually get multiple subsets. Now the multiple subsets, what you're doing is that you are deriving the subsets based on the criteria, okay? So in this paper, they use 3 criteria. So support, accuracy, and length. So in this subset, you will calculate the average support of all the rules that are found in here. And then any rule that has a support greater than the average, you put it in here, okay? So you have this. And then you do the same for accuracy, you have another subset. You do the same for length, you have another subset, okay? And then you do the same for these ones. So here you also have 3. Now, once you've done that, you look at the rules that overlap these subsets, right? You look at the rules that overlap these subsets, and that becomes your rule for that group. And ultimately, when you combine the rules that you have here, that becomes the rules for your data set. So now what this is really trying to do pictorially is that you are, in this particular case, you have 3 criteria and you're trying to find the rules that are in this sweet spot, okay, that satisfy the criteria that you have. Now, of course, you can add as many criteria as you want, or you can reduce the number of criteria. And again, my answer to how many you should use is you are the data miner, you get to choose. Now, the thing is that the more criteria that you use, the more circles that you have, and the less likely you are to have rules that satisfy all the criteria. And so you probably end up with having no rules. The less criteria you use, say if you use 2, then you are probably going to end up with having a huge amount of rules, which comes back to the same problem that we had. So you really are not determining the best set of rules. So for a problem like this, in practice, generally you may do something like a search. So you may implement a search algorithm that tries to find, first of all, how many criteria you should use and which criteria you should use, okay? So, and again, from the research perspective, this is the problem that researchers try to solve from that angle. In industry practice, you may try a few of these, you may try a few numbers until you get one that works for the problem that you are trying to solve. So once you have that, the intersection of that gives you the logic rules that you use for the data set. So as far as specialized framework is concerned, there are a few more, and we cover a few more in the subject delivery on campus. And so I entreat you all, if you want a bit more, we'll definitely discuss a lot more of these specialized frameworks in the subject. So are there any questions at all at this point?
No, it all makes sense. It's you don't
good.
know what you don't know, and once you hear it, it's cool.
Okay, sounds good. So in general, just to give a bit of an outline of what we've done. So I think we started by looking at the purpose of knowledge discovery. We saw 3 main things. In other words, defining the business objectives, and then identifying the tools that we need, and then also actually really discovering the knowledge. And then in terms of the techniques, we saw several techniques. So we can split them into 2 types of techniques, the supervised and unsupervised. Supervised being that each of the records within the data set are labeled. Unsupervised means that we don't have labels, okay? So maybe I touched a bit about unsupervised. So when we talk about unsupervised, supposing we have records of individuals, and we don't know what we are looking for, but we just want to see whether individuals form some sort of a group. Now, a very good example is one of the projects that I was involved with was trying to find out social groups of people on a social network. So like Facebook. So we try to find out put people who are similar in terms of things that they like, things that they talk about into groups, and see whether there are any interactions across groups. So one research that I have read in this area is, and in fact, colleagues did this work. They tried to look at the vote yes and vote no campaigns, right? I think in 2017. So they tried to look whether people, groups of people in social media, say, for example, this is vote yes and this is vote no, when people interact, whether there are any interactions between these groups of people, okay? Now, again, these interactions are represented by edges, and then the individuals are represented by nodes. So the interesting thing is that if, well, first of all, the first thing they realized was that the interaction between this group and this group was very limited. So that tells us something. That tells us that there is what we call echo chambers within these groups. In other words, they propagate information that they just know. So people don't learn information from other people. So if this would be a social problem and we want to intervene, then we might want to introduce links between these groups and get these groups talking so that people can understand themselves better rather than just echoing what they already know. So that's an interesting application of clustering. So in this case, we did not know necessarily who belonged where, but based on the characteristics, we put them together and then we suddenly form these types of groups. So, so in terms of techniques for knowledge, there are so many of them. Unsupervised learning, clustering, that's one of them. We've just discussed decision trees. We can also talk about, or we also talked about interestingness of discovered knowledge. We said that sometimes we have several rules, and the important question to answer is, okay, which rules are more important? Which one should we pay attention to? So there are several metrics of which we discussed 4. Then, of course, we looked at how all of this plays within a case study. And of course, we looked at a specialized framework. So putting all of this together, I think so far in the sessions, the first session, we looked at introduction. Second session, we looked at decision tree classifiers. This session, we've looked at knowledge discovery. Next week, what we're going to look at is how we put all of this together into a system, a functioning system that helps to make decisions. Are there any questions at all?
There are, thank you. Thank you for the lecture. Charles has asked about something that we covered last week, which was how to decide which decision tree algorithm to use. And I suppose it's another maybe answer.
Yeah, yeah, that's
maybe some factors in it. I don't know.
It really depends on the data set. So I'll just give an experience. So one of the projects that I was working with, I needed to make a prediction based on text data, and for that I needed to use support vector machines. It's one of the classifiers, and there are various types of support vector machines, so various implementations of support vector machines. And for those two, they each gave me different results. And so one of them worked better than the other. Now, ask me why. It is in the details of the implementation of the algorithm. And so it is not so easy to say which is better. It depends on the implementation of the algorithm, and then it depends on the data set you're really using. And so in practice, generally what you would do is that you may try a few algorithms. So first of all, when you have a problem, you may look at a problem. Is this a classification problem? Is this a prediction, a regression problem? Is this a clustering problem? That narrows down to the set of tools that you would be using, okay? So you know all these machine learning tools. You look at a problem, what type of problem, that narrows down to the set of tools that you may be using. Within the set of tools that you may be using, you may have candidate tools that you actually use. And there, you may use previous experience, or you may try each of the tools on a small section of the data set to see which one is actually giving you better results. And as you develop your results, you go more in the direction of the algorithm that gives you better results. But this is where, when you understand how the algorithm works, sometimes that takes a little bit, the guesswork a little bit away, because then you understand the advantages of the algorithm based on how it has been proposed, and then you can choose suitably. So yeah, it's a maybe, sorry.
No, maybe it's fine. Doug's asked about the 4x
Yeah.
Whether there's any sort of software tools or packages that are useful.
So Forex++ was developed by Zahid. I think they have a Weka implementation. I'm not very sure, but it's something I can check with Zahid. And then I think they should have a Weka implementation of that. And so if you want access to that tool, yeah, sure.
So it's not just manual evaluation?
No. So it is an algorithm. So it is an algorithm. And actually, if you know a bit of Python, you could also implement this algorithm yourself, really. So this is the steps in the algorithm. And if you just wanted to use the software package, then somebody must have developed it and put it somewhere. And I'm hoping that Zahid must have done that and put it somewhere so they could just borrow the package and use it. So this is the algorithm. I only went through the steps manually so that if you wanted to code it by Python or Java, you know the steps to do it.
Well, thank you for that. Robin's asked an interesting question. Is data science all about technology and algorithms alone? Or do you look into manual types of analysis alongside to sort of reach a consensus of ideas, i.e. the Ishikawa or iceberg analysis model?
So a couple of things. So data mining or data science, you are using tools to solve relevant problems. Okay, now that actually makes a distinction between a software engineer and a data miner, because a software engineer can implement all the tools. Like, give a software engineer a problem or a task and they'll do it in 3 minutes. A data miner needs to understand the problem, to understand what tools to use. So there is a bit of analysis in there. And then once you use the tools, there is also a bit of analysis about what the tools are actually yielding and whether it makes sense. I'll give you an example. So one of the works that I did, I built a model, and the model was giving me 90% accuracy. And I was like, oh, sweet, I have a beautiful model. Now, a couple of days later, I really looked into why I was getting 90% and I wasn't getting those beautiful figures previously. And I realized that I had a problem, a class imbalance problem. So class imbalance problem means that you have more instances or more records in the data set belonging to one class. So in the previous example I showed, generally you would have more people not having cancer than you would have more people having cancer. So if you sample 1,000 people, then you may have maybe 10 people having cancer and then 990 not having. If you build a model on that data set and you say, oh, well, my prediction is 90%, then you are not a really good data miner, even though you have 90%, because that is telling you nothing. Because if I did a random guess on that data set, the random guess will also be 90%, because probability is 90 out of 900 out of 1,000. So it's not just about the techniques, it's also about analysis and whatever helps with that analysis. Yeah, hopefully that answers it.
Yeah, thank you. Hamilton asks, what's the difference between group and dataset rules?
Group and dataset rules?
Yeah, is there a difference?
I'm not sure what he means. I assume he's referring to this when I was talking about Forest ++. If that is the case, then the groups, so in the algorithm, you divide the logic rules into groups. Now the groups are based on the class values. So in the previous example, we wanted to predict whether an individual has cancer or doesn't have cancer. So we can group the rules based on whether the rules are predicting cancer or not. So for example, if I say tobacco agestio, being yes implies cancer, C, and then I have another rule that says alcohol implies non-cancer. So these are two rules, right? And I can put these two rules into two separate groups, the cancer group and then the non-cancer group. So this one goes into this rule, into that group, and this one goes into that group. Now, so the algorithm analyzes each of these groups, and then in the end, what it does is that of the rules that have been selected from each of these groups, it combines them into one bigger group, and then calls that the data set rules. That's what that means.
Cool, thank you. A question about supervised and unsupervised. Is that the same as structured and unstructured? Or is that different?
No. So when we talk about supervised and unsupervised, that means that for supervised, your records have a class label. Unsupervised, your records don't have a class label. So in this cancer data set that we're using, we know the individuals. I'll just go to that data set. We know we have the label, right? We have, so here we have the label. Now, so if we use this for training a model, that becomes a supervised model because we have given it the label. Supposing you had this data set and you didn't have this, okay? You didn't have this, all right? And all you wanted to do was to find patterns within this data set. So for example, you wanted to find out whether people who drink alcohol and smoke tobacco are similar in other attributes. So in terms of, say, for example, age. So in that sense, you don't have any label. And what you would do is to define a distance between each of these records and put the records together into groups. So for example, you may say, okay, I want 3 patterns from here. And then you may say, oh, this one goes into this group because this has chronic high 95. This goes into another group because it has different values. This goes into another group because it has different values. This one is closer to the first group, so I put it here. And then you do that and that and that until you have populations here. So in this case, you don't have a label, but you are putting them based on some distance metric. Okay, so that is the difference between supervised and unsupervised. Structured and unstructured, generally when we talk about structured, we are referring most often to the relational model. Relational model is nothing but a table, okay? So we're talking about data represented as table. Now, when we talk about unstructured, generally we are talking about data that has no fixed form. So in this table, this is structured. I can have high, but I cannot have high and low. It wouldn't make sense. Or I cannot have a sentence or something like that. So it is fixed as to what values it can have, okay? So the values are determined by the domain values of the attribute. In unstructured, a good example is free-form text, okay? So free-form text, if you write a sentence, blah, 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 is going to school, whatever, there is no constraints as to how that information is put. So a typical example of unstructured data that we analyze would be tweets, for example, or Facebook posts or newspaper articles. Those are considered unstructured because they don't satisfy some fixed constraints as tables do. So that's a basic difference.
Thank you.
Hopefully that, yeah, okay.
Yeah, no, that's great. How about just one final question for the night?
Okay.
And then I'll throw to you for the answer and maybe to take us out and say good night. And thank you so much for a really interesting lecture. And thanks everyone for coming. We'll take us out with Annie. How do you know when to apply regression, classification, clustering, or other techniques? And I'll just cheekily say here, well, I think you should sign up for the course, and particularly this subject. But yeah, is there any advice you have there? And thank you.
Okay. So when we do regression, the aim is to predict numerical or continuous variables. So here, okay. So we need to understand data types to get into that. But here we say these are categorical because the values are nominal, they are words, okay? But if you had, instead of diagnosis, you had, for example, rather probability of cancer, then you know that probability would go from 0 to 100, or maybe 0 to 1 if you are like me. So in this case, you would say that the values are continuous in this interval, and therefore your values can be 0.1, 0.2, 0.11111, and so on and so forth. So when we say regression, we are trying to predict numerical values in that sense. So often you would have a regression line like this, and this would be your probability. And then this would be, let's just say these are your attribute values, all right? So if inflammation is chronic, then that goes to this line, and that line points to a probability value, and this probability can be between 0 and 1. So regression is generally used for getting, predicting continuous values. Classification is used for predicting categorical values, values that have distinct, that are, let's say, discrete. So in that sense, diagnosis, you only have 2 values possible. If this would be color, you'd have however many colors you want to predict. So if there are 3, red, yellow, green, that'll be 3. So in that sense, we refer to that as classification. Clustering, you can use it for either numerical or categorical. The only difference is that in clustering, you don't have the label, and so you're trying to put things together as best as you can based on a distance measure. I think these were the 3 things, right?
They were the 3. And,
okay,
and I guess the question is, how do you know when to apply it? So how do you know when to apply them, Michael?
How do I? Okay, so that depends on the problem. So in this case, I would not apply regression because this is, the target variable here is categorical. So regression will not make sense to me unless I wanted to convert this into binary and then say 0 and 1, which will not make sense because you would end up, you would not have a continuous line. You would end up having something strange, yeah? So in this case, it's, the question more so is the type of task it is. So classification task refers to predicting categorical variables. Regression task or regression analysis refers to predicting numerical variables. So you know based on the class variable you try to predict. Hopefully that makes sense.
No, it really does. And I think I would just add that how do you know when to apply them? You train with Michael, you become an expert and you practice. This is the only way to get it. You're going to, because of course you wouldn't have been born knowing this, Michael. You would have had to learn this, wouldn't you?
Absolutely.
So, Robin, the next, Robin's asked in the chat about when the grad cert starts, and that's next year, isn't it, Michael?
Yes, that's correct.
Okay.
So that's next year. I think it starts in 2020-30 session. That is March.
Yep. Lacey just put it in the chat. That's good.
Yeah.
Yeah. So check your local guides, and if you are interested, feel free to get in touch, and we can point you in the right direction. You know, I love helping people come up with good study plans. Michael clearly loves teaching about it. And yeah, so in the meantime, just hopefully you keep on enjoying this short course. It's been a really interesting session, Michael. Thank you.
Thank you very much.
Next week.
My contact details are on the last page if anyone wants to get in touch as well.
All right. Well, thank you. Good night, everyone.
Thank you.